So a big question that happened last period was they asked, why are we even going to be doing this? And so a place where it's used is it's mostly used in organic chemistry, because basically what we're doing is we're taking what we know about combustion reactions, we're taking those products, we're collecting the products. We know a mass of kind of what we started with, but we don't know what we started with. And you can figure out the empirical formula or what the makeup of that original stuff was. So for our purposes, we're figuring out the fuel. For organic, you could figure out like the protein makeup of certain things or the nitrogen found in certain things. There's lots of applications. It's more on the organic side, so there is a reason and there is a purpose that people use this. But going into what we've got to do, so for combustion analysis, we always have to refer to our combustion kind of reaction, which we know starts with a fuel. And it combusts in a bunch of oxygen. And what are your products every single time? Yep. Perfect. CO2 and water. There are ones that have the nitrogen, but don't worry about that. All right. So the big picture here that you guys have to do is that you'll know some sort of a mass for this, okay? But more importantly, you're going to know the mass of this guy and of this guy, okay? To try to figure out this formula, right? The problem is you see that oxygen appears in all three of these, right? So we can't really measure our oxygen and figure out its part. We got to figure out the carbon and hydrogen. Those are always your first two that you start with, okay? What we do is we make this big assumption that all of the carbon becomes carbon dioxide, okay? Right? Because there's no other place it can go. Conservation, right? And all of the hydrogen has to become what? H2O, exactly, okay? And then some of the oxygen will kind of go between them. Some of the oxygen that it combusted in is going to get added to those, okay? So we're going to see the mass also increase, all right? But this is the big picture here. So what you're going to be doing is you're going to look at the grams of these guys to figure out grams or moles of those guys. And it's all going to come back down to empirical formula. So as a quick review for empirical formula, okay, because in the end, this is the last step. You've got to find your empirical formula, right? So empirical formula, we're not going to necessarily be starting with percentages this time. This time you're going to have the grams, right? What do we need to convert all of our grams into? Moles. Once you have all of your grams and moles, you're going to do what? Divide by the smallest. There you go. Okay. No, we divide by molar mass to get the moles. All right. So you're going to divide all of them by the smallest, so now you have a ratio. And remember, those answers are your subscripts. And don't forget your little special rules on that if you get 0.5s or 0.3s. This one you might get a 0.6, just because these are AP level. So just know that those get multiplied by 3. Okay? But I can help you with that all the time. All right. Okay? So in the end, this is what you have to come back to. Okay? All right. So I'm going to zoom back into number 2. I'm going to move this off the screen a little bit. Okay. Okay, so for number 2, it says a 4.24 gram sample of carboxylic acid, okay, so it means it's composed of only C, H, and O, is burned. The reaction produces 6.21 grams of carbon dioxide and 2.54 grams of water. The compound was found to have a molar mass of approximately 180. So we have a lot of numbers given to us up there. That's the part that's overwhelming, right? So start with what I told you guys to start with. Start with your reaction here, all right? So we have some sort of a fuel that's made up of these 3 guys. Notice I'm using XYZ because I don't know what those numbers are yet, okay? But I have some sort of a compound made up of all 3 of them. I add it to some oxygen because it combusts, And I'm for sure creating carbon dioxide and some water. Okay? Okay, so it says it's a 4.24 gram sample. So I'm just going to put the 4.24 here so I can kind of keep track of what that number represents. Okay, so this is like drawing yourself a picture. Okay? And then it says the reaction produces 6.21 grams of carbon dioxide. So I'm going to put 6.21 grams of this guy and 2.54 grams of water. So do you notice that this side over here weighs more than what this side appears to weigh? Do you guys see that? Why? What am I not considering in this number? Yeah, all the oxygen that it's taking from the room. All right, so all that oxygen gets used and it's creating these compounds. So that's why the masses look like they get bigger. Okay? All right. That always bothers like a certain number of people and they're just like, what? Why? So that's where it's coming from, okay? So this oxygen we consider in excess. You don't know completely what that means yet. We're going to get to that in this next chapter. All right. All right, so we are assuming all of that carbon became carbon dioxide, all that hydrogen became water. So we're going to start with that. What about this 180 thing over here? What is that going to be used for? Look at what the question's asking for. To find the what? No. It's the molecular formula. Good. So why don't you guys circle that and label it with the molecular formula? Okay. So that's not until the very, 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 very last step. You have to find empirical formula first. You always have to. Okay? All right. So we're going to start with some carbon dioxide. We're going to start with that guy right there. Okay? And our goal is that we need to somehow go from grams of carbon dioxide to grams of carbon. Okay? That's what we're trying to do right now. Okay? So we're going to start with the 6.21 grams of carbon dioxide. I'm going to bring my words down to the right. Can I go straight from grams of carbon dioxide to grams of carbon? No, who do I probably have to change into first? Most likely the mole. Right, good. Okay, and then I bring those words down to the right. Notice I'm not putting any numbers in yet because we'll come back to the end and do that. Let's lay out our game plan here. So we have moles of carbon dioxide. Now who can I compare that to? Moles of, who are we trying to get into? Carbon, right? Okay. Because we need the empirical formula. So we need moles of carbon eventually. Empirical formula, you need moles of every single piece. And you divide by the smallest to figure out your subscripts. Got it? Yeah. Cool. All right. So then we're going to bring words down to the right. Just so you know, my AP students sometimes stop right here, get their moles, kind of push it off to the side because they know they need it for empirical formula. So that's always a step that you can sit there, you can write moles of carbon so that it's done and ready to go. I'm not going to do that in our notes because it'll confuse you. All right, so we're going to keep going. So we're going to have moles of carbon, bring that down to the right, and who do I need to convert into? Grams. That was our goal, right? We need grams of carbon. Okay. All right, so when we go to fill this in with our numbers, we have this mole-gram combination here. What do I put for the moles every single time? 1. A 1. I have another mole-gram one way over here to the right. What do I put in for that one? A 1. Good. Okay. All right, what do I put for the grams part? The molar mass, exactly. So get your molar mass of carbon dioxide, shout it out when you got it, and we'll get a second on it. going to miss it. What is it? We're going to go with that one. Okay. All right, 44.009. All right, cool. And then grams of carbon over here is what? That's easy. Just read it right off your periodic table. Yep, 12.011. Is that what your guys' says? Okay, 12.011. All right, and then right here for the carbon to carbon dioxide. So what the heck am I going to put right there? What do you guys think? You guys remember? We had a couple homework problems on this, huh? Well, not coefficients, because this one, yeah, it's your ratio. It's like your subscripts, right? So how many carbons are in one carbon dioxide? Only one, right? So this one is a 1-to-1. What if that top number or top letter? What if this was oxygen instead? What would you have put up there? A 2. Okay, so remember, once you're in moles, you can use coefficients, you can use subscripts, you can use basically whatever you need to use, okay? All right, so in one of these, there were only 1 carbon. So you can see for the water, we're going to be changing. It's not going to be a 1-to-1. All right, so go ahead and calculate that. So remember, you multiply all the guys across the top. So you have a lot of 1s in this one, so this is pretty easy. You just got to do 6.21 times the 12.011. Push equals and divide by the bottom.
I can't read the remember next to grams.
44.009. Okay, sounds good. We'll go to 4. That's fine. Okay. All right, so this right here, what is this number representing? What did I just find? This is just grams of carbon. Good. Okay. All right, cool. So the next step is we got grams of carbon. Now we're going to use our grams of water to figure out grams of who? Hydrogen, exactly. Perfect. All right, so we're going to do grams of water to figure out grams of hydrogen. And just so you know, once again, this is where the older kids, sometimes they stop at moles, get that number, write it off to the side, and keep going. Because eventually you need moles of everybody. That's what you need for empirical formula. All right, so let's get going on this one. So I'm going to move through this one a little bit quicker this time. All right, so we have grams of water. And the amount that they're giving us is, can someone remind me? I can't see it on mine. Oh, 2.54. Got it. Okay. All right, 2.54 grams of water. I'm going to bring my words down to the right. Change into moles. So I know that 1 mole of water is, it's about 18.02. Okay. I'm going to bring my words down to the right here. What am I changing into? I have moles of water on the bottom, so I need to change into moles of hydrogen. Good. All right, this is not where you include diatomic stuff. Okay, that would be if I was asking about hydrogen gas. Hydrogen gas is H2. Okay, but this one I just want to know how many hydrogens, how many H's are in H2O. There are 2. Good. So this is a 2 on top, a 1 on the bottom. So there are 2 H's in every 1 H2O. Okay, then I'm going to bring those words down to the right. I'm going to do grams of hydrogen on top. So biggest mistake people make right here is they once again, because I have just drilled it into your heads that you can't forget your diatomic, they double up their mass. Well, you just doubled up moles and the mass, and that just screws everything up. So don't do that. We're only talking about 1 hydrogen here. So 1 mole of hydrogen is about 0.008. That's right. Okay, cool. All right, go ahead and multiply those. Let's get our grams of that. So this one is a 2.54 times 2 times 1.008. Push equals, divide by 18.02. If you notice, I skip all the ones. Good. 0.284. Perfect. All right, so from here, awesome. We have grams of carbon, we have grams of hydrogen. What is the last piece of information we have to have before I can even solve for empirical formula? We need grams of oxygen. All right, so what do you guys think you want to do? So use these masses and add them together? Yeah. I think you're saying that. All right, so we have the 4.24 here was given to us, right? So we take our 4.24, which is our total. We're going to subtract carbon. We're going to subtract the hydrogen. Because basically what you just found was how much of that hydrogen came over and became water. How much of that carbon became water. So whatever's left over has to be grams of oxygen. So once you get that, can you shout that one out? Because I forgot that number. I think it's 2.263? 61, okay. Awesome, cool. So we have a lot of information here. Do you see that? Sweet. So what do? Nope, those are all grams right now. Everybody needs to be in moles, okay? So I do apologize if you're running out of room because I'm totally going to zoom out and use my extra space that I have. All right, so you're going to remember the shortcut is you're dividing by their molar masses, right? So this one will just be a 12.011. So this is where that step that my AP sometimes does, it'll save you a little bit of time because if you just find the moles real quick and then convert to grams, then you at least have both numbers at the same time. All right? All right, so right here, I'm going to do it the long way on that one and the short way on the other two. All right, so for moles of carbon, what is everyone getting? Zero point what? Cool. And for hydrogen, you should have divided by 1.008 to get I'm sorry, what? That's fine. And then finally for oxygen, we're going to divide that one by the 15.999 to get Okay, so now what's our next step? We have moles of everybody. We divide by the smallest, which for two of them, it's the same number. Yay! And you can probably figure out this guy. How many hydrogens are there? 2, yeah. So this is 1, approximately 2-ish. Actually, it is 2. It is actually. And then a 1. So we have CH2O. And that is your empirical formula. So what's part 2 of the question? What do you have to do? Huh? You have no space. That's okay. If you use the top part, you'll have some space. This top one is a short problem. So for the next part, it wants the molecular formula. So remember, you do molecular formula mass divided by empirical formula mass. Okay, so you should have 180 on top, and carbon is 12 plus 2 is 14 plus 16 is what? What's 14 plus 16? 30, thank you. So, what is 180 divided by 30-ish? 6. Come on, you guys. 18 divided by 3. You got this. All right. So we have 6, so we would multiply everybody by 6. We would get C6H12O6, and that's your molecular formula. And we're done. Okay? All right, so your game plan for number 1. Okay? Number 1, they give you your sample size. Can everybody see it okay? We're all okay? Okay. They give you a sample size, and they tell you how much carbon dioxide you made. So this one, instead, you don't have to write this down, but it's a CH compound plus some oxygen makes some CO2 and H2O. So we are given 1.50 for that. We're given 4.40 for this guy. So your first thing to do is we're going to take that 4.40 grams of CO2, and you need to find grams of carbon and moles of carbon, right? Eventually you got to find moles. That's why might as well just get it done. Once you have that, now you're going to take that 1.50 and subtract your grams of carbon to get grams of hydrogen. And then the grams of hydrogen you convert to moles of hydrogen. And then from this point, now it's empirical formula. And that's where you stop. Yep. So the top one should not be as strenuous.